Recording in progress.
So good afternoon. This is lecture 7 of the course entitled An Introduction to Linear Algebra Using Python. My name is Dr. Richardson and my email address is listed below, srichards22@comcast.net. So organizationally, you're reminded that learning is not a passive activity, so please take notes, whether looking at the lectures in real time or the video clips. That way you will be able to convince yourself that the concepts and ideas that we're going through step by step make sense. You're requested, strongly urged to do the problem sets. They have an analytical part as well as a Python lab exercise. That's really the only way to understand the concepts. Just by looking at the lecture notes and not doing the problems, you're not going to get much out of the course. You're encouraged to ask questions and send me email questions. Send me questions by email at srichards22@comcast.net anytime during the week, 7 days a week, and I promise to get back to you within 24 hours. And you may find a ruler to be useful in doing the problem sets and also during lecture. So we were looking at vectors last time. And in particular, we were looking at the problem of multiplying vectors. We were looking at a number of things, but I just want to pick up from our discussion of multiplication of vectors to point out something a little bit more clearly. So imagine you have a vector in 3 dimensions, has 3 components, u, and another vector v, and it's also in 3 dimensions, and it has 3 components. And we discussed last time in lecture 6 that we, as well as a great deal of other folks in science and engineering, find it useful to write these vectors as matrices in column representation. So U is a 3x1 matrix whose matrix elements are as follows. V is a 3x1 matrix whose matrix elements are as follows. And you can ask yourself the question, what is the dot product of U with V? So if you look at our earlier discussion in lecture 6 and part of 5, you can simply write this down as a scalar. It's the sum of 3 scalars, and each scalar is the product of matrix elements of the respective matrices. Now, we said last time, and we'll come back to this, vectors are matrices. So I could recast this definition of the dot product of 2 vectors in terms of matrix multiplication. It's just the transpose of the vector U, which is a 3x1 matrix, times the vector V, which is a 3x1 matrix. And if in fact you use the rules of matrix multiplication to do this, again, assuming that your matrices or your vectors rather are written in column representation, and this is what you're asked to do. This is in fact the transpose of U. It is a 1x3 matrix. This is V, and she is a 3x1 matrix. So you can do matrix multiplication. The rules are satisfied. The column index of the first matrix equals the row index of the second matrix. And you should get a 1x1 matrix. A 1x1 matrix is just a fancy way of just describing a scalar. And that's exactly what the dot product of two vectors is. At the end of the day, it's a scalar or a number. So I just wanted to come back and circle around that point. Okay, so last time we talked about basis vectors. So I want to revisit these guys again. And in particular, we talked about a class of vectors known as, a class of basis vectors known as the standard basis vectors. Extremely important. And this now. So again, we start from the beginning. You have the set of all points in a line that's described by R1, and you can define a vector, V. And it is an object that has a direction given by its unit vector and a magnitude given by its component V sub x. We also discovered an alternate way of writing this, where E hat sub 1 is the same thing as the unit vector I sub hat. It's a different form to write the same thing. Why we want to go through this exercise, we'll see that later on today's lecture. In this case, if you write this in a component form, it's just a 1-by-1 matrix. And so I hat or E hat 1 is a very special basis vector. And that's what it is in one dimension. Now in the plane, the set of points in the plane is described by R to the R superscript 2. So here you could write the vector one of two ways. You could write it in column representation, or you can recognize that you can generate it from a basis. E hat 1 times V sub x plus E hat 2 times V sub y. And again, I'll just say this now, but I'm not going to repeat it. These are the same things. These basis vectors are the same thing as I hat and J hat. They're unit vectors. Excuse me. The important point here is that my vector V, I could write as a component V sub x times E sub hat 1, which is just a 2-by-1 matrix, and V plus V sub y times, so V sub x times E sub hat 1, and I add that to V sub y times E sub hat 2. And it's easy to prove to yourself when you do the scalar multiplication and the vector addition, you basically get the vector in column representation. Enough space for that. Well, let's give us a little bit, let's give ourselves a little bit more space. This is in column representation. Okay, so again, E hat 1 and E hat 2 are standard basis vectors. They're standard because they really are the most fundamental set of basis vectors you can have. We'll talk about other basis vectors later in the course. And finally, last time we looked at the problem of all points in three-dimensional space. So here you could write your vector in column representation. It is a 3x1 matrix. And if you want to write that in an alternative way, using basis vectors, is e hat 1 times v sub x plus e hat 2 times v sub y plus e hat 3 times v sub z. So clearly the standard basis vectors are e hat 1 is the 3x1 matrix that looks like that. E hat 2 is a 3x1 matrix that looks like that, 3 rows in 1 column, and E sub 3 hat is 0, 0, 1. So E sub 1 hat, E sub 2 hat, and E sub 3 hat are the 3 standard basis vectors in R3 in 3 dimensions. So that means that you could write your vector V as a 3x1 matrix in column representation. And that's just V sub x times E sub 1 hat plus V sub y times E sub 2 hat. I may have been misnaming those guys. It's E sub 1 hat. It's not E sub hat. And then there's the component V sub z times E sub 3 hat. I may have misspoken before. My apologies. Okay, and it's easy to see that when you do the scalar multiplication for these 3 terms and add them up, you in fact get that. So in a way, any vector is built up from basis vectors. So we can take all of these 3 observations and put them in a nice simple sentence to get a better idea of what we mean by basis vectors. A set of basis vectors are, by definition, linearly independent. We talked about linear independence in lecture 6, and you know how to prove if a set of vectors are linearly independent. So I would suggest that you, in fact, go and do that. Show that in R1, show that in R2, and show that in R3, the basis vectors are linearly independent. So a set of basis vectors are linearly independent, and they span or generate all points in either R1, R2, or R3. Those are the examples we've looked at so far. Now, as I said last time, it's really very helpful in linear algebra to just look at pictures, geometric representations of what's going on, in addition to just writing out things analytically. And in the problem sets, I have referred to Grant Sanderson's excellent lectures on linear algebra. There are a number of them. We're not going to go through all of them in this course, but the few that we're going to refer to, I have highlighted in the problem set, and I would definitely suggest that you look at these videos. They've gotten well over 2 million hits over the last couple of years. They really are very beautiful. Okay, so we're still talking about vectors. So again, some of this may be a review, some of this may be new. That's okay, as long as we eventually were on the same page. I want to look at other important properties of vectors. So it's important to figure out what all the properties are of vectors, and then you can go ahead and use them, as in the problem set in future applications. So one important concept about vectors is the idea of orthogonality. It sounds like a big scary word, but it's not. So for example, I hat, the unit vectors I hat and j hat are vectors that when you take their dot product, that's the same thing as taking the dot product of e hat 1, e hat sub 1, and e hat sub 2. That's a better way of saying that. That equals the number or scalar 0. So if you have vectors u and v, excuse me, and they are vectors either in 1 dimension or 2 dimensions or 3 dimensions, and if the dot product of u with v is 0, but as we saw before, that's the same thing if you look at these vectors as matrices, as this, which is equal to the 0 matrix, which is just a scalar. So you may say that's nitpicking, but it's an important distinction to make here. So if this is true, if those two statements are true, then u is said to be perpendicular to v, or u is orthogonal to v. So clearly, I hat is orthogonal to j hat. By definition, that's how I set those guys up. The unit vector I hat points in the positive x direction. The unit vector j hat points in the positive, unit vector I hat points in the positive x direction, and the unit vector j hat points in the positive y direction. Okay, there's another important concept that we will introduce at this time. And that's the concept of orthonormality. And let's just define it in words, and we'll look at an example in a minute. Vectors, so orthonormality exists when you have a set of vectors that are both orthogonal to each other and each one has a magnitude or length or norm of 1. So, for example, in R3, the standard basis vectors e hat 1, e hat 2, and e hat 3, these are all vectors that, in addition to being basis vectors, they're orthonormal. But remember what they are. And vectors are matrices, so you can write these in column representation as follows. Here are the standard basis vectors in R3. And what you can see is if you pick any one of these vectors, e hat sub 1, and dot it into e hat sub 2, you'll get the Kronecker delta. That is to say, this equals 0 if I and j are not equal, n equals 1 if I equals j. Furthermore, so that just says they're orthogonal, but orthogonality tells you something even more powerful. Not only are these vectors orthogonal to each other, but the magnitude, length, or norm of each one of them is 1. And please check this. These are easy things to verify. So please check that. Okay, so this ends our discussion or review of vectors. So let us return to our discussion of matrices. So we needed these tools, we needed this background, because we're going to go back and look at everything we've done in lectures 1 through 5 in a more compact form. So from lectures 1 through 5, we can write down the following. Matrix equation. We have seen this before many, many times. A is what we called our coefficient matrix. X is our matrix of unknowns. And capital B is a matrix which we refer to as a constant matrix. So I remind you that in fact, this equation is a very compact way of writing down a system of linear equations. It's a very easy way to write it. So you can write it out as distinct equations, but you can all boil it down to a simple matrix equation. So this is an extremely important relationship in linear algebra. Next, we're going to simplify it a bit. So suppose A is a square matrix of order n, then I'm going to recognize that if A is an n by n matrix, X has to be an n by 1 matrix, and using the rules of matrix multiplication, B has to be a n by 1 matrix. So these are all matrices. It's a matrix equation. You have matrices on one side and you have matrices on the other. On the left-hand side, you're multiplying matrices together to get a matrix on the right-hand side. Now, we spent all this time talking about vectors, so let's use these. Since vectors are matrices, we're going to replace the matrix X by the vector X. And I can do that since vectors are always matrices. All matrices are not vectors, but all vectors are matrices. And so that's what I can do for the matrix of unknowns. I can write it in terms of a vector. And I can take the constant matrix B and write her in terms of a vector lowercase b. And again, I can do this since vectors are matrices. So this equation can be recast as perhaps one of the most important equations in linear algebra. So one of the most, in fact, for purposes of this course, it is the most important equation in linear algebra. So this is one of the most important equations in linear algebra. And that equation is that the matrix A can be multiplied by a vector X, and that will give you a vector B. So note that in our case here, A is a matrix of order n, so it has n rows and n columns. X is a matrix that has n rows and 1 column. So you can multiply these guys together because the column index of A is identical to the row index of X. And my result, the matrix, or the vector B, it's really a matrix, and it's a matrix that has n rows and 1 column. Star, star, star. And it's important to realize that buried in this is a very compact way of taking all those systems of linear equations that you want to solve simultaneously and boiling them down to a simple matrix equation. So we now are at the stage where we can sit down and, well, sit down, but we can sit on a platform that's 37,000 feet in the air and look down on what we've done before. We can generalize all this for the case where A is not a square matrix. It has M as in Michael rows and N as in Nancy columns. So we've gone a far distance from Kramer's rule, which only works if the number of equations equals the number of unknowns. So in fact, let's check to see that that makes sense. Here's one of our most important equations in linear algebra. In the box. On the left-hand side, you are taking a matrix and you're multiplying it by a vector. So the left-hand side is matrix vector multiplication. And on the right-hand side, you get a matrix or vector. Okay. All vectors are matrices, not all matrices are vectors. And again, I'm doing this in the most general case. I could have I could let A be a matrix that has M as in Michael rows and N as in Nancy columns. Then the vector X has to have N as in Nancy rows and 1 column. And then the rules of matrix multiplication tell me that the vector B must have M as in Michael rows and 1 column. So this general expression applies for 3 cases. A could be a square matrix. The number of rows equals the number of columns. It could be a tall matrix where the number of rows is greater than the number of columns. Or it could be a wide matrix where the number of rows is less than the number of columns. Okay, so we really are just simplifying everything we've done in the first 5 lectures. And to see that in a concrete fashion, I want to go through some case studies. So the first case study I want to look at is, suppose the matrix A is a square matrix of order n. It has n rows and n columns. And again, this is really important. I'm sitting down here now and summarizing everything I've done in the first 5 lectures, but I'm putting it in a very simple, compact notation. That's the beauty of linear algebra. It takes very complicated expressions and it writes it in simple forms. And that approach is applicable to lots of different fields: statistics, computer science, physics, mechanical engineering. So it helps you really figure out what's going on. Okay, so again, we write down one of our most important equations in linear algebra. We know the size of these matrices. And let us look at, in this first case study, the situation where if A were a non-singular matrix, then by definition, that means its determinant is 0. And it also means that A must have an inverse. So if that's the case, in this particular case, no pun intended, I can calculate, evaluate, either longhand, Gauss-Jordan elimination, or Python, the inverse of A, left multiply both sides of this equation by A inverse, and remembering the properties of multiplying matrices when one of them is the inverse of the other, then, well, let's say that becomes that, and that's the same thing as that. I now have an exact expression for my unknowns. Namely, the unknown vector is just the inverse of A times the vector B. I know this. I always knew that. I can possibly calculate this. And at the end of the day, I can solve my system of linear equations simultaneously by just doing this matrix multiplication on the right-hand side. So if in case one, if A is a square matrix, and if A is non-singular, as a typo here, if it's non-singular, it means its determinant is not 0, sorry. And then if that's true, then its inverse exists. So this tells you immediately that for this problem, you have a unique solution. So if you want to figure out whether a problem has a unique solution or not, just look at A. And if A is non-singular, you're fine. That means that the inverse of A exists. And if you actually want to calculate it, then you need to figure out how to calculate the inverse of A, which we know how to do. And then we know how to put these two guys together in terms of matrix multiplication. We know how to multiply matrices, and we can get our answer, the vector of unknowns. Okay, so that's case 1. Let's look at a second case. And that's, you can obtain that, but just sort of looking at case 1 and, sort of turning it upside down. So suppose A is a square matrix. Order n. But now its determinant is 0. So it is a singular matrix. That means that its inverse does not exist. So that means it doesn't have a unique solution. So only one of two things can happen. In this particular case, you'll either have an infinite number of solutions, or you'll have no solution. And this makes sense with case 1. So this makes sense with respect to case 1. Okay, so let's move forward. So I have case 1 where I write down my important formula from linear equation. And I look at two situations where A either has an inverse or it doesn't have an inverse. So again, here's the equation that rules the day. This is the star of the show. Okay, so let's look at case 3. What other possibilities can we deal with or explore? Well, suppose A is a square matrix. It's a matrix of order n, so it has n rows and n columns. But suppose now the constant matrix is just the zero matrix. Okay, what would be the solutions of this matrix equation? Well, clearly, there is a trivial solution. For x. And that trivial solution is just the zero vector, because 0 times A, the matrix A times the matrix 0 is definitely going to give you the zero matrix. And, just think of some examples and check that. Make sure you believe that. Now, what about non-trivial solutions? So suppose there exists a non-zero solution to this matrix equation, for which this matrix equation, again, you're taking a matrix, multiplying it by a vector, and getting a matrix or vector. Suppose there exists a non-zero x for which this equation is true. Okay. Then there's a very logical conclusion that you can reach. A cannot be invertible. It can't have an inverse. Why is that? Well, if A were invertible, then you would be able to write down this simple matrix equation. And you sit down and stare at this for a minute, you realize that this is impossible. There is no matrix in this part of the galaxy, or in the rest of the universe for that matter, that can bring the zero matrix, probably a better word is transform. There's no matrix in the universe that can transform the zero matrix to the vector x. So this has a very important consequence. In other words, if the matrix A times the vector x gives me the zero vector or zero matrix, both of those are synonymous, then there only exists a non-trivial solution if and only if the determinant of A is 0, or if A is singular. So this is an extremely important theorem, if you will, that is used in science and engineering many often, and I'll give you more practice on this in a future problem set. Probably problem set 7 and definitely problem set 8. Okay, so we've looked at 3 possible cases. And again, we're just summarizing everything we've done in the first 5 lectures. Now you can imagine another scenario where the matrix A times the vector X gives you the 0 matrix or 0 vector. But in this case, A is tall or wide. It has m rows and n columns. Now you're still okay, right? Because A is an m by n matrix. She has m as in Michael rows and n as in Nancy columns. X has to have n rows in 1 column. And my 0 matrix has to have, watch it now, has to have m rows in 1 column. Okay. Otherwise, you just can't fall asleep on the basic rules of matrix multiplication. The column index of the first matrix has to be the same as the row index of the second matrix. And then what you're left with is an answer that has m rows, m as in Michael rows, and 1 column. So what can you do for this particular scenario? Well, we know this. We've seen this creature before. We have used the idea of the rank of a matrix to, in fact, determine what's going on. If you calculate the rank of the matrix A and then calculate the rank of the augmented matrix, still an augmented matrix, it's just that this thing on the right-hand side is the 0 matrix. If this is equal to n, where n is the number of unknowns in the problem, and look, this is consistent, right? Go look at our matrix or vector X. It has n as in Nancy rows in 1 column. So it has n unknowns. If this is true, then a unique solution exists. The second possibility is that the rank of A could be equal to the rank of the augmented matrix. This is still an augmented matrix now, just because it has a 0 to the right-hand side of the vertical bar doesn't cause us any problems. It's still a matrix. It's a 0 matrix, right? Well, if this is less than n, where n is the number of unknowns in the problem, then an infinite number of solutions exists. And finally, if in fact the rank of A is less than the rank of the augmented matrix, then no solution exists. So again, we have solved problems like this, lots of problems like this, but what we've done here in case 4 is recognize that all those problems could be boiled down to this simple matrix equation here, where A is a matrix X is a vector, and you get a result 0 vector. So I'm just highlighting these guys. I'm not calling them anything new with new notation. Okay, so those are 4 cases. And finally, if you think about it, there is a 5th case you can write down for what's going on, but I will essentially stop here for a break and we'll resume in 5 minutes.